Today we're going to talk about qualitative techniques. That is, we're going to discuss slope fields. Before we begin, I'd like to do a review of what we discussed last time. Last time we talked about analytic techniques, that is, the method of separation of variables. Remember that more generally, we do want to construct a mathematical model. There are three key steps to constructing a mathematical model using a physical situation. First, we'd like to identify the key variables, such as position, velocity, or even population size. Second, we want to articulate the principle that underlines the problem under investigation. For example, this might be Newton's second law of motion, that is, F equals ma. Third, we need to identify the initial conditions. This might be the initial position, or perhaps even the initial velocity. Whenever we have both a differential equation and a list of initial conditions, we call this an initial value problem. In this course, we're going to discuss three concepts: analytical techniques, qualitative techniques, and numerical techniques. Analytical means we want to find an equation that governs the situation. Qualitative means we want to describe the behavior of the solution. And numerical techniques means that we want to perform some type of arithmetic in order to find the solution. We defined a differential equation by first looking at derivatives. That is, given a function y, we'll call its derivative dy dt, or we'll also denote this as y prime of t. The quantities dy and dt are called differentials. We say that a first order differential equation is an expression of the form dy dt equals f of t comma y for some function f of two variables. We'll think of t as an independent variable and y as a dependent variable. That's because we're looking for a solution y equals y of t. A solution is simply a function that satisfies the expression y prime of t equals f of t comma y of t. In this course, we have three main goals. First, we want to present some analytical techniques. That is, we'd like to exhibit some first-order differential equations which govern a physical situation. Second, we'd like to present some qualitative techniques. That is, we'd like to describe the behavior of our solutions. And third, we'd like to present some numerical techniques. That is, we want to perform some type of arithmetic in order to find the solution. We realize that up to this point in the course, we've looked at four types of differential equations. The first is looking at an object falling under gravity. The second is looking at an object falling under gravity, but we have drag coming from air resistance. The third is the exponential growth model, and the fourth is the logistic growth model. Notice that all four of these appear in the form dy dt equals g of t times h of y for some function g that's only a function of time alone, and some function h that's only a function of y alone. Such equations are said to be separable. And in fact, if g of t is a constant and not really a function of time, we say that our equation is an autonomous equation. There's a relatively simple numerical technique in solving such separable equations. First, bring all of the y terms to the left-hand side and all of the t terms to the right-hand side. This gives us an expression of the form 1 over h of y dy equals g of t dt. Second, integrate both sides. This gives us an expression of the form capital H of y equals capital G of t plus a constant c. This will turn out to be an implicit relation, so our final set is to explicitly solve for y as a function of time. Now today we'd like to move on to some new concepts. That is, I'd like to discuss the concept of a slope field. Before we get there, let me give you a motivating question. Say that we have a rocket of mass m which blasts off from the surface of the Earth, perhaps at an initial velocity v0. Gravity pulls back on the rocket no matter how high the rocket goes, so is it possible that the rocket can ever leave the Earth and go to another planet? It turns out that the answer is yes, and in order to do so, we need what's called the escape velocity. This is the velocity that a rocket must reach so that the pull of gravity is too weak to force the rocket to return to the surface of the Earth. That is, if the rocket has an initial velocity v0 greater than the escape velocity, then it will never return. So here's our new motivating question. The space shuttle has an initial velocity of 28,900 kilometers per hour, which roughly translates to 5 miles a second. Can the space shuttle travel fast enough to escape the pull of gravity? Well, we'll answer this question today. Of course, what we're going to do is take a look at a physical description of what's happening, and then we'll write down a differential equation. But here's our philosophy for today. It is not necessary to find the exact solution of a differential equation in order to understand how the solution behaves. To this end, let's try to work backwards a little bit to understand what's really happening with derivatives and even with differentials. We're going to discuss the differences between a secant line between 2 points and a tangent line at 1 point. Let's consider the plot of a function x of t versus time t, where we'll plot the position x on the vertical axis and we'll plot the time t on the horizontal axis. Through any 2 points on the curve, we can draw a line segment. That is, given 2 points, call them t0, x0, and t1, x1. The line through them has a slope that looks like the change in x divided by the change in time. We can write this as x of t1 minus x of t0 divided by t1 minus t0. Of course, if these 2 points are very close to each other, then we can actually find the slope of the tangent line. Another way to say this is the limit as t1 approaches t0 of this ratio, x of t1 minus x of t0 divided by t1 minus t0. We just simply write this as the derivative and say that this is dx dt evaluated at t0. In particular, the slope of the secant line is a really good approximation to the slope of the tangent line. So we can say that the change in x, delta x, is approximately the slope, dx dt, times the change in time, t. Conversely, if we knew the slope, x prime of t, at every point t comma x, then we could do a reasonable job of sketching the path x of t versus time t. This is called the direction field or the slope field. We'll give some examples to explain this phenomenon. Let's consider a function x says that its derivative dx dt is equal to 0 for all time t. Physically, this means that we really have an object with no velocity, so we expect its position to be a constant. That is, x of t equals x0 must be a constant function. Well, we can plot these tangent lines that have slope 0, and we can also plot the solution x of t equals a constant x0. What you see here on the screen is the following. We have arrows that denote that everywhere we must have a slope of 0. These arrows are all flat. They all have slope 0. Another way to think of this is, for every time t, we can consider a position x. This is a point here in this grid, that is t comma x. And at every point, we want to consider the slope, namely dx dt. So at every point, we place an arrow, and each of our arrows has slope 0. The blue arrows here is what we call a slope field, and the black line that you see is a plot of the solution x of t equals 0. Let's consider another example. Let's consider the equation dv dt equals negative g, as in the case of gravity. Well, we know that the velocity must be a linear function. That is, the plot here must be a straight line. V of t equals v0, the initial velocity, minus g times t. We can plot these tangent lines, that is the arrows again, where we have constant slope v prime of t equals negative g. And we can plot our solution v of t equals v0 minus gt. Here, just like before, we have arrows that denote the various slopes. At every t comma v, we place an arrow. That is, here in this grid, we have time that's on the horizontal axis, and we have velocity that's on the vertical axis. We place an arrow, and the slope of this arrow is dv dt. Because dv dt is a constant, is a negative number, negative g, we see that each of these arrows must be pointed in a direction that denotes negative slope. Now, if we connect the arrows together, then we actually find our solution. This is where the black line is not only where we've connected the arrows together, but it's also plotted the function v of t equals v0 minus g times t. Let's consider a third example. Let's say dv dt equals negative g minus gamma over m times v. This is the case of gravity, but we want to keep track of drag coming from air resistance. Note that the slope will change as v changes. That is, if we take a look at the right-hand side of this expression, negative g minus gamma over m times v, this really is a function of v. So depending on where we have our velocity v, the slope dv dt will be different. Let's do something similar just like before. We'll plot these tangent lines, that is the arrows again, where the slope of the arrows is v prime, which is negative g minus gamma over m times v. And we'll plot the solution v of t just by connecting the arrows. Once again, we have various points here in this grid. The time is along the horizontal axis, and the velocity is along the vertical axis. You can see here that at every point t comma v, we have an arrow. But now the arrows will be in different orientations depending on what's happening for v. Remember that the arrows have to have direction minus g minus gamma over m times v. So for different v's, we will have different orientations of the arrow. You can also see that we can connect the arrows together to find this black line. This black line is the solution to our differential equation. Note, we can actually see something else from this slope field, the equilibrium solution. That is, this is the solution where the derivative of the solution is zero. It's just the same thing as saying take the right-hand side and set it equal to zero. The equilibrium solution is the line, the constant line, v is equal to negative mg over gamma. We can actually see this directly from the graph because it's the asymptote. It's the one where we have the arrows all are flat with slope zero. Now let's go back to our motivating question that began today's lesson. What about the space shuttle? Here's our goal. Say that we have a rocket that blasts off from the surface of the Earth with an initial velocity v0. We'll derive a formula for the escape velocity and then use this to determine when such a rocket will be able to escape the gravitational pull of the Earth. We're going to use Newton's law of gravity and Newton's second law of motion to give the following initial value problem. Here we have mass times acceleration equals the force due to gravity. And we want to make sure that we are starting off from the surface of the Earth, so x of 0 should be 0, and we'll have some initial velocity v of 0 equals v0. You can see here on your screen various quantities that we'll define, but we won't really need both of these. I'll say here that lowercase m is the mass of the rocket, lowercase r is the distance between the center of the mass of the rocket and the center of the Earth, but we can just really work with the variable x, which tells us the height the rocket is from the surface of the Earth. It'll be useful for us to consider lowercase g, which is the gravitational acceleration, which is 9.81 meters per second squared. We wish to solve this differential equation, but unfortunately we've only discussed how to solve separable first-order differential equations. So we're going to perform a trick to reduce to that case. Let's take a look at the left-hand side and the right-hand side of this differential equation separately. First, let's take a look at the left-hand side. Here we have mass times acceleration. We'll use the fact that the acceleration is dv dt, and then use the chain rule to express dv dt as dv dx times dx dt. Now, dx dt is just the velocity v. So we find that mass times acceleration is m times v times dv dx, which we can write as the derivative d by dx of some function, namely 1/2 mv squared. Now let's take a look at the right-hand side. Here we have negative capital G times lowercase m times capital M divided by lowercase r squared. Let's substitute in our expression for lowercase g and also substitute in our expression for lowercase x as lowercase r minus capital R. We'll find that this here is equal to the derivative d by dx of mg capital R squared divided by x plus capital R. This may seem a little bit strange, but we're writing this so that we can integrate both sides to find 1/2 mv squared equals mg capital R squared divided by x plus r plus a constant c. We can determine this constant c by using the initial values here of the problem. Remember that when t is equal to 0, x equals 0, and v equals v naught. So putting all of this together, we find that the implicit solution to our initial value problem is the expression that you see here on your screen. The left-hand side is just the change in kinetic energy, and the right-hand side is the change in potential energy. Now let's step back for a moment and remember that here for today's lesson, we really want to consider the slope field. If we go back to our original differential equation and now express things in terms of velocity and position, we'll ignore time for the moment. We then have a plot that looks like what you see here on your screen. Here, along the horizontal axis, we have the height x, and along the vertical axis, we have the velocity v. Here, for every arrow, we're plotting in the value dv dx that corresponds to this function f of x comma v. You'll see that as we connect the arrows together, our solutions actually break up into two types. First, we have what happens if we have an initial velocity, that is when the height is 0. Our initial velocity v0 is less than some quantity. These are what you see as the orange lines. The orange lines seem to be following all the way down to v equals 0. Here what's happening is we have a rocket. The rocket then starts at the surface of the Earth. It moves up a little bit, but then the Earth's gravity pulls too much and the velocity drops to 0 so that the rocket turns around and falls back down to the surface of the Earth. Again, the orange lines tell us if the initial velocity is not great enough, then the rocket will fall back down to the surface of the Earth. The gray lines, on the other hand, say if the rocket is moving fast enough initially, then its velocity will always remain positive, and therefore the position x can continue on indefinitely. The position x will go off to infinity. You can see this by just connecting the arrows. Again, the gray lines tell us if the initial velocity v0 when x is equal to 0 is high enough, is large enough, then x will go off to infinity and the velocity will always remain positive. I'd like to point out a philosophical concept here with this graph. Notice that time t does not appear. That is, we can actually view this as a relation between the independent variable x and the dependent variable y. Here we're thinking of the velocity as a function of the height. That is, now we're not really thinking of things here as a function of time. Notice that here's the idea. The higher up we move, the slower the rocket becomes. So the higher the height, the less the velocity. We'd like to make sure that we can still move the height as far as we want and the velocity won't become 0. That's the concept of an escape velocity. I'll say that once again. As time increases, we want to make sure that our position x increases without bound and the velocity at least remains non-negative. This means that the rocket can travel infinitely far away from the Earth and never reverse its velocity. We can put all of this together by saying that the change in the kinetic energy and that equals the change in potential energy must be bounded between two different numbers. Here we'll just take a look at the limit as t increases without bound. The first say that v of t must be greater than 0. So on the left we see that this is greater than negative m v naught squared. On the right, as t increases without bound, x of t goes to infinity, and so we find minus mgr. This means that if we'd like to make sure that our rocket travels infinitely far away, then our initial velocity must be greater than a certain number. This number is what we define as the escape velocity. It's roughly 7 miles a second. So let's go back to our motivating question. Is it really possible that we can reach the escape velocity in a commercial jet plane or even the space shuttle? Unfortunately, the answer is no, and here's why. A commercial jet plane can fly between, let's say, Los Angeles and New York in around 4 hours, whereas the space shuttle can cover the same distance in about 5 minutes. So, really, we might as well just focus on the space shuttle since it travels much, much faster than any commercial jet. By measuring how fast space shuttles have traveled, we see that the initial velocity of the space shuttle is roughly 5 miles a second. Unfortunately, 5 miles a second is less than the escape velocity of roughly 7 miles a second. That means that the space shuttle's initial velocity is much too slow to break free of the Earth's gravitational pull. So, this means that not only can the space shuttle not break free from the Earth's gravitational pull, it cannot even travel to other planets, such as Mars or even the Moon. Thanks very much for watching.